Hey there, this is Professor Hank. Welcome back. In this video, we are going to examine the theory behind the heap data structure. So let's begin. So the heap data structure is a data structure that is made using a binary tree. The binary tree that implements the heap is going to be complete, with the exception of perhaps the last level, right? Every level of the tree is going to be full before starting another level. And the last level of the tree does not have to be full, okay? But values will be added to the tree from left to right on the bottom level. And as soon as the bottom level is full, we start another level. All right, so a fundamental property of the heap is that each child node has a value less than its parent. So two types of heaps. One type is a maximal heap, and that's a heap where the biggest value is always in the root node. Okay, that's one of the benefits of a heap, is that you can always instantly identify where, if it's a maximal heap, the biggest value is. It's always going to be in the root node. So getting or retrieving that value, very fast operation. Minimal heap is the opposite of a maximal heap. It has the smallest value within the entire data structure, always located within the root node. Okay, well, in this video, we're going to look specifically at a maximal heap, but everything that we talk about is applicable to a minimal heap as well. It's just we'd be sorting the heap from the smallest value to the largest rather than from the largest to the smallest. Okay. All right, so most often a heap is implemented using, or in memory, it's implemented using a partially filled array, right? It's a binary tree that gets represented or gets stored in memory in an array, okay? All right, so here's some key formulas that make that work. Okay, we can always find the index of a child node by using one of these following formulas, right? So since the tree is stored in an array, there's going to be this relationship between the parent node and the child node, where the value of the parent node is stored in one element, and then the children are going to map to that element's index, right? So the way it works is that the index of the element holding the left child node is going to be equal to 2 times the parent index plus 1. And similarly for the right child, that index for the element holding the right child node is going to be 2 times the parent index plus 2. Okay. All right, so we can go in the reverse order. We can find out which element is storing the parent node if we use the child or the child's index, and do a little bit of math, right? So the parent index, the index of the element in the array that holds the parent node, is going to be equal to the child index minus 1, and divide that difference by 2. Okay. All right, so here's some basic operations we'll define. Insert, we will add a value to the heap. Okay, now, after doing that, it could be the case that our heap no longer adheres to that fundamental property where the parent has to have a value greater than both of its children. So after doing an insert, we have to run an additional algorithm, and we'll call that algorithm the reheap up algorithm. And that algorithm is used to rebuild the heap after an insertion is done, making sure that that property, that fundamental property heaps, is restored. Okay, we'll have top, and top is simply going to retrieve a copy of the maximum value in the heap, assuming it's a maximal heap. Okay, otherwise it would retrieve a copy of the minimum value in the heap. Okay, then we're going to have remove, and remove is going to remove the top value in the heap, the maximum value in the heap if it's a maximal heap, or the minimum if it's a minimal heap. So after doing a remove, we're going to have a call to another algorithm called the reheap down algorithm. And what that does is it rebuilds the heap after removal is done. So again, it could very well be the case that after removing a value, our heap is no longer a heap because it doesn't stick to that property, right? That fundamental property. So reheap down is used to rebuild the heap and make sure that that property holds once again. Okay, so let's look at the insert algorithm in a little bit more detail. Okay, so here's what's going to happen is that the new value is going to be added at the bottom of the heap. Okay, so then once we've assigned that value, we'll increment the bottom. And then after this is done, we'll call reheap up to rebuild the heap. Okay. All right, so what about the reheap up algorithm? Well, the way this thing is going to work is it's going to start with the bottom node. Okay, and then we're going to identify its parent. And if the child node is bigger than the parent, we're going to swap them. Otherwise, we'll quit. Or we'll repeat this using the parent node as the new bottom. Okay, so here's an example of us doing an insertion. Okay, so here we have a heap. You'll notice that the root node is 100 and its two children contain values 90 and 80 respectively. And those three nodes all adhere to the fundamental property of a heap. The parent has a value that's greater than either of its children. Now if we look at the node that contains 90, the heap value holds here too because it has a value that is greater than either of its children. Okay, so now if we're going to do an insert, then what's going to happen is that the new node is going to go at the very bottom. Okay, so in this case, we're going to insert 200. Okay, so in the array right now, the way this would be represented is that 100 would be an element 0, 90 would be an element 1, 80 would be an element 2, 75 would be an element 3, 85 would be an element 4, and then 200 would be added to element 5, right? And we'd have to have a variable, which we say we can call it bottom, which would keep track of where the bottom value is in the array. Okay, all right, so after we've inserted 200 though, take a look, the heap property is no longer holding up, right? Because 80 is not greater than 200. So this is where the reheap up algorithm comes into play, right? We have to rebuild that heap, right? So here's what's going to happen, right? We'd identify who the parent is. In this case, it's going to be the node that contains 80. And if the parent value is less than the child, which in this case was 200, then we're going to swap them. Okay, and then we'll repeat. So now we'll identify who the parent is, and the parent is going to be 100, right? And we can identify that by doing that math using the formula that I shared in the previous slide. Okay, but anyway, so we've identified the parent. Okay, and once we've done that, we just say, okay, well, is the parent node, does it have a value that's less than the child? And the child in this case being 200. Yes, it does. So we're going to swap them. Okay, and once we've done that, the heap has been rebuilt, the value has been inserted, and we're good to go. Okay, now let's take a closer look at this in memory. Okay, so I had talked about the mapping of the different nodes to each other using those formulas, right? So you can determine who a child is of any node by multiplying the parent node's index times 2, adding 1 to it, and that'll get you your left child. And then for the right child, multiplying the parent's index times 2 and adding 2 to it. So here, if we look at the node 100, right, its index is 0. So who are its children? Well, 2 times 0 plus 1 is 1. So that means that 90 is the left child of 100. Okay, who's the right child? Well, 2 times its index, 2 times 0 is 0, plus 2 is 2. So its right child, the right child of 100, is 80. Okay, so that's how that works. All right, so let's go ahead and go through the memory here. And right now, bottom is storing 4, right? So that indicates that that is the element that holds the last value in the heap, or the bottom of the heap. Okay, the top is always going to be element 0. Okay, so if we're going to add 200 to our heap, then what we have to do is we have to increment bottom, okay, and then we'll assign the value to the bottom. All right, so then once we've done that, it's time to start calling the reheap up algorithm to rebuild the heap. Okay, so what we're going to do is identify the parent of our new node, which is 200. So how do we do that? Remember that formula. it is the index of the child node minus 1 divided by 2. So 5 minus 1 is 4, divided by 2 is 2. So the parent node of 200 is 80, right? So what we're going to do then is say, okay, well, is 200 greater than 80? Well, yeah, it is. So we're going to need to swap those guys. Okay, so now we repeat. And this time, the node containing 200 is treated as the child. So who's its parent? Well, take the child's index, 2, subtract 1 from it, and divide by 2. So 1 divided by 2 is going to be 0, right? 2 minus 1 divided by 2, 0. So the parent of 200 is 100, okay, which is index 0. So is 200 greater than 100? Yes, right? The child's bigger than the parent, so we got to swap them, okay? And so now our heap has been rebuilt. Okay, so what about the top algorithm? Top algorithm, really simple. Simply return the value in the first element of the heap array. That's it. That's all there is to it. Very fast, very simple. Big O of 1 operation, constant time. The array does not change in any way with this algorithm. All right, so let's look at remove. So with remove, what we have is, it's going to be a two-part process. First thing we're going to do is we're going to first swap the first and last elements of the heap array. Okay? And then we'll decrement the bottom of the array, right? And this will have the effect of removing the value from our heap, right? It's a partially filled array. Okay, once we've done that, we'll rebuild the heap by calling reheap down. Okay, so let's look at reheap down in a little bit more detail, that algorithm. So starting with the top node, identify the larger of its children. Okay, so the top node being, the root node of the tree. Okay, if it has no children, quit. Okay, otherwise, find the bigger of the two children. Now, if it only has a left child, then that's going to be the bigger child, right? Okay, so if the bigger child is bigger than the parent, swap them. Otherwise, we're going to quit. Okay, so we'll repeat this, but we'll use the bigger child as our new top node. So let's see that example, right? So here what we're going to do is we're going to remove a value, right? And values are always removed from the top of the heap, okay? So another property of the heap. So in this case, 200's got to go. So what are we going to do? We're going to swap 200 and 80, right? That's the top and the bottom of the heap. Okay, so we'll swap them. And once we've done that, we decrement the bottom variable, and that effectively gets rid of our 200. Okay, but now the heap is broken, so now we got to call reheap down to rebuild our heap. Okay, so first thing we have to do is we have to examine the two children of the top node, in this case 190. Which one's bigger? Well, 100's bigger, so that's our bigger child, and the bigger child is greater than the parent, so we're going to swap them. Okay, now we're going to repeat, but this time 80 is going to be considered the top node. Okay, so then we're going to need to take a look at its children, 75 and 85 in this case. Which one's bigger? 85. So 85 is going to be the bigger child, right? Child's a bigger child. So is that bigger than its parent? Then the top node here? Yep. Is it bigger than 80? Yes, it is. So we're going to swap them. Okay, and then 80 would become our new top node, but since it has no children, we're finished. Okay, so what does this look like in memory? All right, so here's our heap array with the values stored. Okay, and we decided that we're going to go ahead and get rid of, we're going to remove a value. Remember, the top value is always the value that gets removed. So in this case, top value is 200. Top is always that element 0 in the heap array. So first things first, got to swap the top and the bottom values. Then we decrement the bottom, and that effectively removes the last node, or the last value, right, from our array. It's a partially filled array. Okay, but after we've done that, we got to do our reheap down, right? We got to rebuild the heap now. Okay, so What are we going to do? Well, 80 and 100 are going to swap positions. Why? Because between the two children, the children of, the children of 80 were 190, right? Remember that formula for finding the children. And so since 100 was bigger than 80, swap them. Okay, so now our new top node becomes 80, right? So who are 80's children? Well, 2 times 1 is 2, plus 1 is 3. So that's going to be the left child. So 75 is the left child of 80. Okay, right child is 2 times the parent's index plus 2. So that's 4. So the right child of 80 is 85. So who's the bigger of those two? Well, 85 is, right? So what are we going to do? We're going to swap them. Why? Because 85 is bigger than 80. Okay, so then 80 would become the new top node, and since it doesn't have any children. The algorithm's done, right? The heap has been rebuilt. Okay, so that's everything. Let's go ahead and summarize. Just briefly, though, first, let's talk about the complexity of the insert and remove operations. Now, the heap is implemented using a binary tree, and traversal in a binary tree, whether it's a binary search tree or whether it's a heap, is going to be big O of log of n. Now, one of the nice things about the heap is that you're always guaranteed to have a balanced tree. So you never have to worry about the tree becoming degenerate and having a situation where your traversal is going to become big O of n. It's always going to be big O log of n because of this property of the heap. Okay. All right, so we examined 3 operations: insert, top, and remove. And with the insert and remove algorithms, we both saw that we required calling sub-algorithms, right, to rebuild the heap after doing an insertion or a removal. So we looked at reheap up and reheap down, respectively. Okay, so that's everything for this video. Hopefully you found it helpful. If you have any questions, as usual, please feel free to shoot me an email if you're one of my students, or feel free to stop by my office hours. And please also, if you thought that this video was useful or helpful in any way, please consider hitting that thumbs up or hitting that subscribe button. Really appreciate it. And if you thought it sucked, well, there's that thumbs down button for you too. Okay, well, thanks for watching, and we'll catch you next time.